just finding derivatives using product rule and quotient rule.
Yeah, those you should be able to verbalize. What's the function?
All right, so it's 4 minus 3x.
That it?
Minus x squared.
What was that? Plus x squared?
No, minus.
That it?
And then over x squared minus 1. So I just don't know how to do it.
Quotient rule. Do you have it memorized?
Yeah, it's uv prime, or high d low minus, well, uv prime minus vu prime over x squared.
Over u squared. In other words, the way I remember it is you start with the bottom and you end with the bottom squared. That's all you have to remember. If you remember that expression, then you can't really get it wrong, right? In other words, if I'm going to start with the bottom, then I'm going to start with x squared minus 1. Well, what has to go next to that? The derivative of the top, right?
Yeah.
What's the derivative of the top?
Should be negative 3 minus 2x.
And then I know that order is important, so I must be subtracting, as opposed to with the product rule, we're always adding. So with the product rule, you don't care if it's u v prime plus u prime v or vice versa. But with the quotient rule, you do. It matters that you have it correct on this part. So this part here has to be just the reverse of this.
Right.
Okay, so instead of the bottom times the derivative of the top, it's the derivative of the bottom times the top. And let's put it in brackets because we are subtracting things.
Right.
So the derivative of the bottom is what?
2x.
Times the top. All over the bottom squared. And the best way to do the bottom squared is just like that.
Yeah.
Okay? Now, there's definitely some simplification that needs done.
Yeah.
Let's FOIL those two.
All right.
See what we get. Just do it term by term, and I'll write it as you say it.
Okay, so negative 3x squared.
Okay.
Plus 2x.
Okay. One thing when you're foiling, I feel much more comfortable if you use a steady method that's the same every time.
All right, sorry. Yeah, okay.
That times that plus that times that.
Yeah. Okay.
Now, you are going to have a plus 2x at some point, but if we do it out of order, we may forget a term.
All right.
So let's do the second term first, which is minus 2x cubed.
Plus 3.
Plus 3. And now plus 2x.
Yes.
Just, I like to do it that way because I'm not going to make a mistake.
Yeah.
And distribute the 2x. And what I've done is replace my bracket with a parentheses. So what is 2x times that?
8x minus 6x squared minus 2x cubed.
And now the next step is to remove the parentheses, combine all like terms. How many x cubes do we have in total?
2.
Well, what are they, I mean?
Oh, well, negative 2x cubed and negative 2x cubed.
Actually, this one turns positive. In other words, when we remove the second set of parentheses,
we have to distribute
that negative sign to every term. So what I really am going to have is minus 2x cubed plus 2x cubed.
Yeah.
How many x squareds do I have?
Well, now you're going to have 3x squared.
That takes care of that one and that one. How many x's do I have?
Minus 6x.
And any numbers?
And 3.
Plus 3. Okay. And the bottom is still x squared, what was it, minus 1?
Yep.
Minus 1 quantity squared. Now let's see. If I remove, let's factor a 3 out from the top. That's going to leave x squared minus 2x plus 1. Okay. And that's useful because that factors into x minus 1 times x minus 1. It's a little useful, so we'll write it like this. And the bottom, if I factor the inside, I get what? What's difference of perfect squares factored?
X plus 1 and x minus 1.
So it's x minus 1 times x plus 1. And we're squaring it, so I'm going to have another x minus 1 times x plus 1. And now I can factor some of those. That x minus 1 and that x minus 1 cancels with those two. And so my final answer is not that complicated.
Yep.
X plus 1 squared. That is the derivative of that function.
Okay.
And then as to whether you multiply the bottom out or not is, that's just a choice. I prefer leaving it like this rather than multiplying that out to get x squared plus 2x plus 1. All right.
Yeah.
In general, quotient rule problems are not laying it out. In other words, this is not the hard part.
Yeah.
That's just following the formula.
Yeah.
The hard part is the hard algebra that comes after that. And
yeah.
It usually is hard algebra, and usually you'll find something in the numerator that will cancel with the denominator, typically.
Yeah.
So that's why you have to do all of the math, combining those two, combining that, and then subtracting them, simplifying them, and see if you can cancel anything out with the denominator.
All right. Okay, so my next problem I wanted to do was of a similar nature, but this one's sort of a little different. It's x squared times, and this is in parentheses, 2 over x minus 1 over x plus 1.
Like that?
Yep.
And that's why. So you need to find y prime?
Yeah.
Okay. Well, what's the easiest thing to do?
Well, I mean, it doesn't say I have to use quotient rule specifically, because I don't know how I would. Would I distribute the x squared out?
And also, just so you're aware of, if I had something like this, I don't have to use the quotient rule on that either.
Yeah.
In other words, I can write that as x squared times x plus 1 to the minus 1. And now I can use the product rule. And the product rule is so much simpler than the quotient rule that I'm frequently tempted to use the product rule whenever I can. But I don't want you to in this particular case, just because they're trying to teach you the quotient rule also. As long as you know that if you can easily write this thing with a negative exponent, well, I can use the power rule on this, that part of it. So I don't need the quotient rule. But there is something else that we should be doing here. Let's distribute this x squared.
Okay. And you would do that as
that will simplify things a lot. So I end up with 2x minus x squared over x plus 1. Okay?
Okay.
Now I can easily take the derivative of that, and then I can take the derivative of that using the quotient rule.
All right.
That's going to be the easiest way to go.
Okay.
Rather than finding a common denominator and doing it that way,
Yeah.
that's the other option that we would have. So
Right.
let's take the derivative of this. In other words, the one advantage of differentiation is if you have a bunch of stuff added or subtracted, you can just take them one at a time.
Yeah.
So y prime is what? Now that I have it in this form. What's y prime of that?
Just 2.
Okay. Now,
This.
only danger here is getting your brackets or parentheses missing. Okay, so let's use the quotient rule. What's the quotient rule again?
It should be x plus 1 times 2x.
And I want to make sure I put that in parentheses. That part. I don't need the parentheses around the 2x, but minus what?
1 times x squared.
All over
X plus 1 squared.
Yeah, let's just leave it like that. A lot of times you can get in trouble if you go ahead and expand that out because you won't see then that you can do some canceling. So let's leave the brackets, simplify the numerator. That simplified to?
2x squared plus 2x.
Minus x squared all over x plus 1 squared. Hold on, let me close my door here.
No problem.
And simplify the numerator again. What's 2x squared minus x squared?
2 plus 2x.
Well, let's see. We still have an x squared. In other words, the 2x squared minus x squared is going to be equal to x squared. So if I erase that, I can erase that.
Oh, okay. Sorry, that was a dumb mistake.
That's all right. And
that's a lot of where my problems come from. It's just like silly algebra mistakes.
Yeah. A lot of people are like that. So
yeah.
Now to simplify it, I don't yet have an x plus 1 up here.
Yeah.
But now let's use a common denominator so that I can combine these two things. And then I might be able to simplify it.
X plus 1 squared.
Well, right, x plus 1 squared. So this is going to be 2 times x plus 1 squared all over x plus 1 squared. That's that part. Minus x squared, and I have to distribute that negative sign, minus 2x. Now notice that the top, what does the top become? Let's see. We have 2x squared plus 4x plus 2 minus x squared minus 2x. So again, we have just an x squared. And we have plus 4x minus 2x, so we have plus 2x plus 2. And this is all over the denominator, which is x plus 1 squared.
All right.
And
then isn't x plus 1 squared the top?
No. X plus 1 squared would be x squared plus 2x plus 1.
Oh, okay. Yeah.
So, I think that's our answer. I don't think we can do much more.
All right. Sounds good to me.
Yeah, I don't see any simplification. I might be not seeing it, but I don't see it. If that was 1, then this whole thing would be equal to 1.
Okay.
Okay.
All right.
But it's not. It's a 2. And that makes a huge difference. It's just like if I had x plus 2 divided by x plus 1. Cannot simplify that.
Yeah. Mm-hmm.
Change one number, and I can. But as long as it's x plus 2 over x plus 1, can't simplify it. Same problem here, as long as that's a 2. And it's possible that I made an arithmetic error, and maybe that is a 1, but I don't, there's no point in going through these problems twice looking for arithmetic errors. You just need to be very much attention to detail when you go through it the first time. And that's the way calculus is going to be, because your typical calculus program might have 10 steps. And if you make a mistake on one of them, you're not getting the right answer. So you really have to try to be a perfectionist when it comes to calculus, as opposed to algebra, where it may only have 4 steps in a typical algebra problem. You still can't get one of them wrong, but much more so with calculus.
Yeah. Okay.
All right. What else you got?
Okay. So this one is, now it says find the derivative of a transcendental function.
Okay.
And it's negative e to the x plus tangent of x.
What's the derivative of just e to the x?
E to the x.
So the derivative of minus e to the x?
I don't really know.
Minus e to the x.
Oh, okay.
Okay. And then what's the derivative of tangent?
Isn't it like secant or cosecant or something?
Secant squared.
And so that's as simple as that problem is?
Uh-huh. Now,
wow.
Let me give you some hints as to memorizing the transcendental functions. What's the derivative of sine?
Cosine.
And notice that cosine is the cofunction of sine. So if I want the derivative of cosine, I know it's going to be negative, whatever the cofunction of that is.
Ooh, okay. All right.
Okay. Now that's sine. You need to memorize that, and it has a positive derivative. Let's look at tangent.
Yeah.
Tangent's derivative is secant squared. You just have to memorize that. Okay?
Okay.
But cotangent, in other words, the cofunction of tangent, first of all, I know it's going to be a negative. Second of all, it's going to be the cofunction of secant squared, so it's going to be cosecant squared.
Okay.
Okay? So I don't have to memorize that one or this one. And the third one I have to memorize is secant, and that's secant tangent is its derivative. And so the last one would be cosecant. Well, first thing I know is it's negative. All 3 cofunctions are negative derivatives.
Cosecant, cotangent, right?
You got it.
Yeah, cool.
So you don't need to memorize that, or that. You can always figure them out. Just remember that the derivative of the cofunction is negative, and whatever this is, it's the cofunction of that also. Now, let's talk about e to the x. That is the only function other than 0 whose derivative is equal to itself. So if y equals e to the x, then y prime equals e to the x.
Yeah.
Have you had the chain rule yet?
Yeah, we've just been touching on it a little bit.
Well, if y equals e to the 2x, then y prime is e to the 2x times the derivative of the inside, which is that, which is 2.
Oh, okay.
Okay. So when you're applying the chain rule to this transcendental function, it's real easy.
Yeah.
Do the derivative of the inside, or, excuse me, it's the derivative of the outside times the derivative of the inside, is what the chain rule is. Okay? And
Right.
the places where it can be a little tricky are places like this. Two different methods are needed to come up. First of all, these aren't the same thing. Sine squared of x is not the same as sine of x squared.
Yeah.
This is sine x times sine x. This is sine
Right.
of whatever x is squared. Well, if I want to take the derivative of that, what's the inside and what's the outside?
Well, x is the outside. So sine squared is the inside.
Well, the inside is sine x. In other words, the way you figure it out is you go through substitution. If I was going to use substitution, I would let u equal sine x. Why? Because then I'm taking the derivative of u squared, and I know how to do that.
Okay. All right.
Okay? For the second problem, if I was using u substitution, I would let u equal x squared.
Okay.
So the inside for this one is sine x. The inside for this one is x squared.
Okay.
So if I'm taking the derivative of this one, I'm going to say 2 times sine of x, that's the derivative of the outside,
All right.
times the derivative of the inside, which is cosine x.
Okay. All right.
The bottom one, if I'm doing it, well, the derivative of the outside is sine of u, right?
Uh-huh.
So the derivative of sine is cosine of u times the derivative of the inside, which is 2x.
Okay.
So
Right.
this particular function is actually an excellent way to illustrate how you get the inside and how you get the outside. The outside's relatively easy. What people have difficulty with is what is the inside?
Oh, all right.
And you can figure out the inside by going through the u substitution process. In other words, by using this technique, it'll tell you what the inside is. Because unless I get the wrong u, in other words, if I were to let u equal x, say, well, that's not going to work either. But if the key is figuring out, can you differentiate the thing after you've used u substitution? In other words, as long as I let u equal sine of x, then I'm going to be differentiating u squared, and I know how to do that. Or in the bottom, where I'm letting u equal x squared, I know how to differentiate sine of u.
Okay.
Okay? All right. So what other problems do you have?
Okay, so this is like the last one, this homework.
Okay.
It's 8 times x minus 2. The x minus 2 is in parentheses. And divided by e to the x. And this instruction is different. It asks me to determine the points at which the graph of the function has a horizontal tangent line.
Okay. What does that mean?
Well...
What would a horizontal tangent line mean?
Well, I know the tangent line's the derivative, so I guess a horizontal...
What would the slope of a horizontal tangent line be?
Well, it would be...
0.
0, right, okay.
Okay, in other words, if we look at slopes,
yeah,
that's a slope of 0.
Right.
That's a slope undefined or infinity.
Okay.
Okay, so when they say, what is the slope of the tangent line, well, what x, we need to take the derivative of this first.
Okay.
Set it equal to 0, and that'll be a horizontal tangent line. Read the question again. What exactly did they want?
Determine the point or points at which the graph of the function has a horizontal tangent line.
Okay. So let's take the derivative of this.
All right. So,
and let's distribute the top. Just make it a little easier.
Okay.
So we don't have to deal with any product rule.
Yeah.
Okay, so what's the first thing?
So it should be e to the x times 8 minus e to the x times 8x minus 16. Ooh, the x minus 16.
All divided by,
E to the x squared.
which is the same as e to the 2x.
Yeah. Oh,
But in this case, I'm going to write it like this. Notice that if I had e to the x times e to the x, I would add the exponents. So I have e to the 2x. I wrote it like this because I can see right away that I can factor out an e to the x from top and bottom, right?
Oh, yeah.
In other words, I can take that out, I can take that out, and I can take one of those out. So now, what's my new top?
8 minus 8x minus 16, or 8x minus 24. Wait.
Remember, this negative sign has to get distributed to that.
Darn it. I forget that every time.
It's okay. So it's really 24 minus 8x.
Oh, yeah.
Did I do that right?
Yeah, you did.
Okay, and we're dividing that by e to the x. That's my derivative. And they want to know where that thing is equal to 0. Well, whenever you have a fraction, it's only equal to 0 when the numerator is equal to 0.
Right? Oh, right. Okay.
So I can immediately set this. In other words, I'm trying to solve this problem. Okay. And the way to solve that problem, well, you can do it algebraically. Multiply both sides by e to the x. Well, e to the x times 0 is still 0. So I end up with 24 minus 8x being equal to 0. Solve for x, you get x equal 3. So at x equal 3, that's the point where you have it, the tangent line to this curve is horizontal.
Oh, okay. All right, that makes sense.
Now, let's just look at that real quick. Let me pull up Wolfram Alpha. I'll plot that function, and we'll take a look at where the tangent line, let's make sure that that makes sense. 8x minus 16 over e to the x. Eight x minus 16 divided by e to the x. Let's see if they like that. Yeah, and the nice thing about Wolfram Alpha is they give you feedback so that you can tell what you typed in.
Oh, okay.
Okay.
This is cool.
As opposed to your calculator, which doesn't do that.
Right. Yeah.
That'd be Inspire. But if you have the TI-84, you, especially if it's a complicated function, it can be really tough to figure out what you typed in.
Yeah.
Okay. So if we look at this, we can see that at 3, that looks pretty close to a horizontal tangent line.
Yeah.
And that's what we came up with, is that at x equal 3, this function has a horizontal tangent line.
Okay.
Okay.
Cool.
All right.
All right. So that was that homework.
Okay.
There's another one that I will flip to shortly here.
Okay.
Okay. All right. So the first problem off of this one was natural log. And then times root x plus 1 on the top.
Is it the natural log of root x plus 1, like that?
Over x minus 1.
Like this?
Oh, actually, no. The ln's or the natural log is in front, and then the whole fraction is put under. It's like the whole fraction is square rooted, not just the x plus 1. And the natural log is multiplied in front.
So it's the square root of natural log of x plus
The
1?
natural log is outside of the square root.
Ah,
Yeah.
but isn't that what I wrote the first time?
Well,
Like that?
no, because like the x plus 1 and the x minus 1 are square rooted.
Ah, both of them.
Yeah.
Like that.
Yeah.
So is that right?
Yeah.
Okay. What's the derivative of natural log?
I don't know.
1 over x. In other words, yeah.
Okay.
If y equals natural log of x, then y prime equals 1 over x.
Right.
It's a key one to remember.
Okay.
Okay? And, all right. And they want you to find the derivative of this, right?
Yes.
And you sure I have it written right?
Yep.
Okay. Well, we can do this a couple of ways.
Well, actually, the natural log's not on the numerator or the denominator. It's just multiplied in front of the fraction, but I don't know if that matters or not.
Okay, when you say multiplied, it's really not multiplication. It's like when you say, what's the log of 6? That doesn't mean log times 6.
Oh, yeah.
It's log of 6 in the way that if I say f of x, that doesn't mean f times x. It means f of x, a function of x. Well, log is the same way. In other words, it's not multiplication. So you're saying the natural log is out front like this?
Yeah.
And this all is in the argument?
Yes.
Okay. Well, this one is, if I'm going to use the chain rule,
right.
What would you be?
Well.
In other words, what do I know how to take the derivative of? Do I know how to take the derivative of natural log of u? Yeah, that's 1. Yeah. That's 1 over u. Okay? So that helps me figuring out what my inside is. So my inside must be square root of x plus 1 divided by square root of x minus 1.
All right.
Okay? So I can rewrite this as saying I've got the natural log of u, and my first derivative is the derivative of the outside, which is 1 over u, times the derivative of the inside, times u prime. You with me?
Not really. I don't understand where you're coming up with all this u stuff from. It's honestly a little bit confusing.
Okay. In order to use the chain rule,
right.
Let's say y is equal to the square root of x squared plus 1.
Yeah.
And I want to differentiate that. Well, I would let u be x squared plus 1. That's the inside, because then I'm going to have y equals u to the 1/2.
Okay.
And I know how to differentiate that. Okay.
Right.
The chain rule, always you have to, if you're going to use u substitution, then you always have to multiply the derivative of the outside times the derivative of the inside, and the derivative of the inside I get from taking the derivative of that. Which isn't going to be pretty, but it's not going to be that hard. But, so, in other words, if I don't want to confuse you by jumping back and forth here, but let's understand how the chain rule works. Okay? If I'm going to differentiate that, well, let's first of all rewrite it without radicals. In other words, if you rewrite it with exponents, it makes it a lot easier. What's the derivative of the outside? Using the straight power rule.
I'm not really sure. Is that just the bottom then?
No, the power rule says that if you have x to the n then y prime is n times x to the n minus 1, right? That's the power
It's
rule.
1/2 x squared plus 1 to the negative 1/2.
You just took the derivative of the outside.
Right.
Now we have to multiply it by the derivative of the inside. What's the derivative of the inside?
2x.
Okay. So that's how you do it. In other words, that's a typical application of the chain rule.
All right.
I could just as easily have looked at this and said, well, I'm going to use u substitution, and I'm going to let u be the inside. So I'm going to let u equal x squared plus 1. So now I have y equals u to the 1/2. And if I differentiate that, I get y equal 1/2 u to the minus 1/2. But now I got to multiply that by du dx, which is the derivative of the inside.
Right.
And that's the way the chain rule always is you're always going to have to multiply it by du dx. Well, what is du dx? Du dx is 2x.
Mm.
So that's how we ended up getting the answer we got. We got y prime was 1/2, and instead of u, let's go back and put in what u was, x squared plus 1 to the minus 1/2, and du dx is 2x. So now I have the full derivative of this equation, which wasn't your problem, but let's go back and look at your problem now.
Okay.
So first of all, the derivative of the outside.
Yeah. Well, outside's the natural log, right?
Yeah. In other words, if I'm going to use u substitution, I'm going to let u equal this whole thing.
All right.
Because then I would have y equals natural log of u. I know how to differentiate that. Y prime would be 1 over u. Okay.
Yeah.
Now I got to take the derivative of the inside. In other words, if u really was this, square root of x plus 1 over square root of x minus 1, now I got to multiply this times the derivative of the inside. So I have to come up with what du dx is.
Yeah.
All right. Let's figure out what u prime is. Using the quotient rule.
Negative. Wait, no, it should be 1/2 x plus 1 to the negative 1/2. Right.
The reason I remember the quotient rule as starts with the bottom and ends with the bottom squared is you cannot get it wrong. If you try any other technique, it's very easy to get it wrong. If I'm starting with the bottom, then I'm starting with that.
Right.
Times the derivative of the top. Okay, with me?
Yep.
Minus the reverse, which is the derivative of the bottom times the top. All divided by the bottom squared, which in this case is very easy. Okay? So that's u prime.
Yeah.
There's a lot of simplification we can do. But before we do that, let's make sure we get this part right. What is 1 over u? Well, it's the reciprocal of that, right?
Right.
So let's just switch top and bottom. So we have x minus 1 to the 1/2 divided by x plus 1 to the 1/2. All times this.
Okay.
In other words, this was the derivative of the outside. This was the derivative of the inside.
Okay.
Now, I can see all kinds of stuff we're going to be able to do here if you want to spend 15 minutes on algebra. But like I said, whenever you use the quotient rule, the hard part is the algebra part.
Yeah. Do I really have to do like this long simplification problem for every problem?
Yeah, you do, actually.
There is a lot of problems here.
Well,
I don't really want to use 4 pages.
Yeah, the problem is if you don't do the simplification, in other words, this whole thing could end up being like 1 or 1 over x or whatever.
Yeah.
That's why we need to simplify it.
All right.
Okay? I'm not saying we have to do that for this. This looks like it could be a hard one to simplify.
Yeah.
Trying to think right off the get-go what we could do. We're multiplying these two, so I could take this x minus 1 to the 1/2 and make this 1/2 again. And cancel it out. Do you see how I was able to do that?
Yeah.
In other words, I had an x minus 1 to the 1/2 in the numerator, and I had an x minus 1 in the denominator. Those combine to x minus 1 in the denominator.
Okay.
Okay. I have an x plus 1 to the 1/2 here. I got 1 over here. That cancels with that. So the simplification process was not nearly as tough as it looked like it might be.
Yeah.
Let's see, we end up with minus 1/2 x minus 1 to the minus 1/2 all over x minus 1 to the 1/2. Well, that minus that gives me minus 1. So I can basically cancel that out. And now I got that. And like I said, it simplifies rather nicely. I now have minus 1 over 2 times x minus 1. And there's your derivative.
What time did you want to end this session?
We can end it whenever you like. If you want to go a full hour, we can. If you want to end it now, we can.
I'd like to go a full hour because there is some more stuff that I definitely need help on.
Okay, I think we probably started close to 7, so let's go to 8. Does that sound reasonable? Okay. What else you got?
The next one is in a very similar vein, but again a little different. So this is going to be negative root x squared plus 1. That's all over x. And that's going to be plus the natural log of, and this is in parentheses, x plus root x squared plus 1.
Well, they are really trying to torture you, aren't they?
God, yeah.
All right. Well, these are two separate things that are being added, so we can take the derivative of that, and we can take the derivative of that separately. Okay?
Quotient.
Yeah, let's use the quotient rule here and the chain rule, because we're going to need the chain rule for this top part.
Oh, okay.
In other words, if I said take the derivative of that, the derivative, well, first of all, let me rewrite it. That's x squared plus 1 to the 1/2. Well, the derivative of that is 1/2 x squared plus 1 to the negative 1/2 times the derivative of the inside, which is 2x.
Alrighty.
Okay, so this thing here is going to be more complicated than it might first appear to do, but let's apply the quotient rule. I'm going to start way over here on the left because I may need that much room. So let's do the first circled.
Yeah.
Let's rewrite it. I'll rewrite it up here. Just always kind of make a habit of rewriting when there's a radical sign there, because the radical sign is never useful in calculus, whereas the fractional exponent is, because you use the power rule so much.
Alright.
Alright, so the circled part. Get me started on it.
Oh, well, this is just where I'm confused, because it's like, do I do the quotient rule first, or do I do the other one first? Like, which one?
Well, this is a quotient that we can't really change, can't simplify it.
Right.
So, got to use the quotient rule.
Okay, so then it's going to be x times
the derivative of the top. What's the derivative of the top?
Well, I guess it would be negative 1/2 x squared plus 1 to the negative 1/2, but then I didn't take the derivative of that inside part, so I don't really...
Do that now, times 2x.
Oh, yeah, that's right. I just throw that on at the end. Okay. Yep.
Okay. So that's the bottom times the derivative of the top. What's the rest of the next part?
Okay, so...
now we know it's the reverse.
Oh, we're still going on the first part. Okay.
Yeah. That's why I wanted to start way left, because I knew I would end up probably going to the right of this page.
Well, that's just 1, so...
Okay.
Really, yeah.
So it's the derivative of the bottom times the top. The derivative of the bottom is just 1, so we have just the top.
Yeah. Which is just...
all divided by x squared. Right?
Yeah.
Okay. Guess I can replace that parentheses and those two minus signs with a plus. Start by that.
Mm-hmm.
And then again, there's going to be tons of simplification to be done. And factoring. I can, let's see, that's x plus that, so I can't factor that x with any of those yet. So let's do that part. And then simplify it after that. Although, like I said, the simplification process is the 15-minute problem. Writing what the derivative is without simplifying it is actually very methodical. As long as you just follow the quotient rule and the chain rule, you'll be fine. So what's the natural log? What's the derivative of the outside of this?
Well, it's just 1 over x, right? Since
it's 1 over whatever's in the inside.
Oh, geez. All right. Okay.
Okay. In other words, if I have the natural log of u, the derivative is 1 over u times the derivative of u with respect to x. Well, I'm going to substitute all of that for u. Okay? The only reason this u substitution is helpful is because it helps you understand what the inside is, which isn't always easy to figure out, especially with transcendental functions. Well, the inside is that part right there. So 1 over that, there's that plus sign. So it's 1 over x plus x squared plus 1 to the 1/2 times the derivative of the inside. What's the derivative of that?
1 plus 2x. Oh wait, no.
Well, you're right. You will be multiplying it by 2x, but let's do the outside first.
1/2 times x squared plus 1 to the negative 1/2, and then times 2x. Oh, so this looks very familiar to the
and then
other one.
Times 2x, exactly.
Yeah.
Okay, so now that's our answer, and it's just a question of can we simplify it.
Yeah.
And rather than spending the time trying to simplify it, I think you'd be better served if we go on to the next problem and get it set up. Because,
yeah.
like I said, simplification is just algebra.
Yeah.
Let me just...
Okay.
In other words, you generally end up with something in your denominator that's in both terms in your numerator, and you can factor stuff out. And in other words, we've got a bunch of, here's an x squared plus 1 to the minus 1/2. Here's an x squared plus 1 to the 1/2. And over here is an x squared plus 1 to the minus 1/2.
Yeah.
And so we can do something with all of those. If nothing else, we can factor out an x squared plus 1 to the minus 1/2.
Yeah.
From both terms in the numerator. Actually, all three terms, because we have one there, we have one there, and we have one there. Okay, so we're going to have three things in the numerator that all have an x squared plus 1.
Yeah.
And you can factor, just, you may not be familiar with factoring when you have a negative exponent, but if I have this, factoring is merely dividing. So I can take out this.
Yeah.
What am I left with? 1 plus, well, when I divide this thing by this, I get just what's left inside there. So after I've factored it, I get this.
Could you explain that whole thing one more time? Sorry, that's really weird.
Factoring is division.
Right.
If I say, give me the greatest common factor between those two terms, I can factor out a 2, which means I got to divide 6 by 2, and I got to divide 8 by 2.
Right. Okay.
That's factoring. Okay?
Yeah.
And notice the common thing in this numerator is x squared plus 1 to some exponent. It doesn't matter if it's negative or not.
Okay.
So I'm going to factor out an x squared plus 1 to the minus 1/2. And what's left over? Well, what happens if I divide each of these terms by x squared plus 1 to the minus 1/2?
One's 1 and 1.
1. But when I divide this by x squared plus 1 to the minus 1/2, notice when I subtract exponents, I get 1. So I get just x squared plus 1. So this is what I've factored out. What I have left over is 1 plus, that's x squared plus 1.
Okay.
In other words, just know that when you're factoring something out, you're dividing every term by it. So the fact that I can factor out something that looks like x squared plus 1 to the negative 1/2, you're not used to factoring out things that have negative exponents, but you can do it. And for the quotient rule, it's valuable to be able to do it because you have to do it a lot of times to simplify.
All right. Okay, so I guess the last problem we'll probably get to is it's the natural log, and then they do the absolute value of -1 plus sine x all over 2 plus sine x.
All of it inside the absolute value?
Yeah, that's right.
Okay. Let's talk about the absolute value.
Yeah.
First of all.
Well, I know it doesn't have like a limit or whatever because I don't know if that's.
If I graph this, y equal natural log of x, it looks like this.
Okay.
X has to be positive. Can't even be 0.
Okay.
But if I want to graph y equal natural log of the absolute value of x, well, now x can be positive or negative, right?
Right.
Because I'm going to take the absolute value of it. So, since x can be positive or negative, that's what that graph looks like. Both of them.
Yeah.
In other words, now I'm looking at the natural log of the absolute value of x.
Right.
Okay. That's the same as if I wanted the derivative of this one down here, it's 1 over x when x is positive, but it's negative 1 over x when x is negative. And you can kind of see why. In other words, the derivative is the slope at any place on this curve, right? So
yeah.
if I wanted the derivative there, it's going to look like that. Well, the derivative on this side is going to be exactly the same slope, only negative.
Right. Okay.
So when I have an absolute value surrounding whatever is in the argument, I can say that the derivative is going to equal whatever it would be without the absolute value when x is positive, and it's going to be the negative of that whenever x is negative.
Oh, okay. So we can just solve it without worrying about the absolute value?
Well, let's make the problem slightly easier by doing the bottom one. What is y prime? Well, y prime is going to be 1 over x whenever x is greater than 0, and it's going to be negative 1 over x whenever x is less than 0, and it doesn't exist when x is equal to 0. You cannot take the natural log of 0, absolute value or not. In other words, x equals 0 is not in the domain here. Just like that equals 0 is not in your domain either.
Okay.
However, that's the only thing that's not in the domain.
Right.
In other words, if I'm doing the problem down below, the easy one, then it's pretty easy. I just do 1 over x for x greater than 0, or for the argument greater than 0, and negative 1 over x for the argument less than 0. And it's not defined at x equals 0. Okay? So basically, we're going to apply that strategy to this. So y prime is going to equal 1 over that thing, which is just the reciprocal of that.
Okay. Right.
Right?
Yep.
Times the derivative of the inside.
Okay.
What's the derivative of, you see why? In other words, I'm applying the chain rule. I'm taking the derivative of the outside, which is this.
Right.
Times the derivative of the inside, which is what?
Well, this is negative 1 plus sine x, right? And then over...
Yeah, I turn the negative 1 plus sine x into sine x minus 1. Just so I...
Oh, yeah.
Yeah, it's the same thing.
Oh.
Okay? It just... I'd rather not have negative in front of stuff if I don't need it.
Yeah, that makes sense.
So now I have to take the derivative of that quotient. What is it?
Yeah. So that's going to be cosine x minus 1.
Hold on.
Or wait,
Always
cosine.
start with the bottom. Always start with the bottom. That way you'll never get it wrong.
Okay.
I realize you can start with the derivative of the top times the bottom. But then that doesn't fit my memory mnemonic. My memory mnemonic says start with the bottom, end with the bottom squared. Well, if I start with the bottom, then I'm going to start with that. That's the bottom.
Right, okay.
Now, I know that the next thing must be the derivative of the top, right?
Yep.
What's the derivative of the top?
Cosine x minus 1.
Just cosine x.
Oh, okay, yes.
Because the derivative of a constant is 0.
Right, okay.
So there's the bottom times the derivative of the top minus, got to be the reverse.
So cosine x again. And then sine x minus 1. All over.
So there's your answer, but the qualification now becomes it's equal to that whenever your argument is greater than 0. In other words, that's only true when x, not x, when this whole argument.
Right.
In other words, when sine x minus 1 over sine x plus 2 is greater than 0.
Okay.
When that, in other words, this is like a piecewise function.
Oh,
The
okay.
derivative is what I have here, that whole thing, but only when this part is greater than 0.
Right.
Well, that's always true, isn't it? No.
Yeah.
No, it's always less than 0 or equal to 0. It's never greater than 0. How can, in other words, the range on sine x is minus 1 to 1.
Yeah.
So there's no way this numerator can be greater than 0.
Yeah.
And the denominator is always positive, even when sine x is minus 1. So if the denominator is always positive and the numerator is always negative or 0, then this is never true. In other words, this whole thing is never going to happen. It's always going to be less than 0, which means the derivative is the negative. I'm just going to put a negative in front of that whole answer.
Okay.
Because
All right.
the argument is always less than 0.
Okay.
Which is
Well, math teacher did
takes away those absolute values.
My math teacher definitely didn't teach us this when he gave us this homework.
Well, this is crazy. This is it's not crazy. I mean, I'm not even going to call it busy work. Is what it is algebra, though. It's not really calculus. We've spent probably 75% of our time in this session doing algebra.
Yeah.
Not doing calculus, okay? So, and it's not like you don't have to do it. You need to be able to do that algebra. But it's unusual that I get a student that has so many problems that require so much time to do the algebra.
Yeah, I know. These assignments have been ridiculously frustrating.
Yeah. Now, you can kind of see one thing I'm going to be able to do here. So I'm going to be able to take that and take away that exponent. So that'll help.
Right, okay.
Okay. In other words, there's some shortcuts you can take for doing the algebra.
And then isn't there like a cosine x minus cosine x over q?
I don't know. I'd have to do some simplification. It looks like this is going to be our new numerator, though. That whatever that is.
Oh yeah, okay. Right.
And we do have a sine x cosine x there, and I got a sine x cosine x there. So one of that's going to cancel with one of those, and we're going to end up with probably just a number. No, I'm still got a cosine x I'm going to have over here also.
Oh. Oh, because you distribute, right?
Right. In other words, I've got to distribute this cosine x to both the sine x and the negative 1.
So it should just be
And I've
2
got to
cosine
distribute this
minus...
cosine x to that too also.
Yeah, so
So
it should just...
I'm going to have a 2 cosine x plus a cosine x.
Plus cosine, right, because that's other negative. Yeah, and
All
then...
over 2 plus sine x times this sine x minus 1. Also in the denominator. It didn't go anywhere. And I don't see any way to get rid of that. There's a sine x minus 1 up here, but that whole thing is being subtracted from that, so I can't really get rid of the sine x minus 1.
Alright, so that's the answer? Just leave it like that?
Well, no, we didn't really simplify it. In other words...
oh, I just meant like, can't you do like a...
Yeah.
Wouldn't it be like 2 cosine x?
That turns out to be... if I simplify this numerator, I end up with 2 cosine x plus their product minus their product plus cosine x.
Yeah.
Well, that's 3 cosine x's.
Oh, yeah.
Okay, so that's 3 cosine x, looks like it's its numerator, and the denominator is sine x minus 1 times 2 plus sine x. And that, and then there's a negative sign in front of that whole thing.
Oh, yeah.
Because the argument is always less than 0, so the derivative is always negative of what it would have been. That's not been true.
Okay. All right.
Okay. Well, good luck with these. I pity you that you got a teacher that gives you a ton of these. I mean, everybody should have to do 1 or 2 of these. But
it's
not 10.
It's like 7 or 8.
Not 10 of them. It's like giving you 3 equations and 3 unknowns. Everybody should have to do that at least once. But if somebody gives you 10 of those, 10 sets of 3 equations and 3 unknowns, each one of those is a 15-minute problem. So you're looking at 2.5 hours worth of work. And that's kind of similar to these. Most important thing you can really learn from this session is that chain rule. Derivative outside times the derivative of the inside. And the best example of how to use the inside and the outside really comes from those 2 functions right there. Because notice, in this case, the inside is sine x, but in this case, the inside is x squared.
Yeah.
So figuring out what that inside is not always easy. If I have e to the square root of x plus 1, well, you know the inside is that. Because you know how to take the derivative of e to the u.
Right. Okay. All right.
All right. All right, Brent.
Okay.
Well, good luck with the rest of those.
Yeah. Luckily we do Thursday, so I got some time.
Okay. And let's see. Your mom scheduled this, I think, by emailing me, or I believe so. You can go directly to my website and schedule sessions if you like.
Oh, okay.
I don't know if you ever did that last year or not.
I
don't think so. I don't know. I can't remember. I think your mom was always scheduling it. Let me just real quickly tell you my website again.
Okay.
Easiest one to use, if you're going to do all online, is Digital Math Tutor.
Oh, yeah, you definitely mentioned
and you can't even misspell it. That's why I like it. It's really a wonderful domain. digitalmathtutor.com. If you go there, you'll see my scheduler, and you can do everything you need to do. Your mom can pay, she can schedule another appointment, whatever you need.
Okay, sounds good.
All right, Brent. Have a good evening. Talk to you later.
Yeah.
Bye-bye.
Thank you. You too.
You're welcome.